It is a universally understood form of modern pain. I mean, you are working on a document, maybe a crucial presentation or, a highly visible message for your team.
Right, something important.
Exactly. And you need to bring in some external information. So you copy a perfectly normal-looking piece of text from an email or a website.
Oh, yeah, we've all been there.
You paste it into your pristine document, and suddenly the formatting absolutely explodes.
It just becomes an immediate structural disaster. I mean, fonts change mid-sentence, the line spacing is completely ruined, and weird hidden symbols appear out of nowhere.
Yeah, and the margins just decide to rebel. You are suddenly dealing with like 5 different indents. The text is inexplicably highlighted in a pale gray that you cannot seem to remove.
It's the worst.
It really is. And it takes you 15 minutes to fix what was supposed to be a simple 2-second copy-paste.
Yeah, anyone who has ever interacted with a computer knows that exact visceral frustration.
Yeah, totally. And that shared everyday annoyance is actually the perfect entry point for our discussion today. Because our mission today is to understand why the simplest file on your computer is secretly the most chaotic.
And how one programmer is using a highly specialized language to tame that chaos.
Right, because we are looking at someone who is actively trying to solve that underlying structural nightmare. And not by, manually fixing the margins.
No, they're doing it at a fundamental programmatic level.
Exactly. We are diving into a blog post published today, June 24, 2026. It is written by a programmer named Eng. And the context here is just staggering to me.
It really is.
This post is titled Notes on Haskell Programming, Part 169, Implementing Initial TXT Export.
Part 169. I mean, documenting a technical journey with that level of granularity is exceptionally rare.
Yeah, that's a lot of posts.
It is. It gives us this incredible microscopic view into the problem-solving process of a developer who is just, working in the trenches.
So, Eng is currently building a console app called XS2 eBook. And the goal of this application is to take documents and export them into various ebook formats.
Which makes total sense.
Right. If you have a document, you might want it as an EPB or like a MOBI format for your e-reader. But in today's specific post, Eng is working on exporting to a plain TXT format.
And this is where it gets really interesting.
Yeah, because this is where I got totally stuck. Eng notes that the input format, the file they are starting with, is already a TXT file.
Right.
So we have a programmer 169 parts deep into a complex Haskell application, building a sophisticated programmatic tool to convert a TXT file into a TXT file.
It sounds like a paradox, doesn't it?
It completely does. I mean, why would anyone need to build a complex tool to do that? Isn't a TXT file supposed to be the simplest, most bare-bones digital format in existence?
Well, that assumption is incredibly common, and it is exactly what Eng's work challenges. We tend to confuse simple with clean or standardized. As Eng explicitly points out in the post, the input TXT format is usually, to use their specific word, dirty.
But wait, when I open a plain text file, I just see letters. There's no bolding, no italics, no weird fonts to mess up.
Right, it looks totally plain.
It is just bare characters on a screen. So how can something that's stripped down actually be dirty or contain errors?
Because you are only seeing the visual representation of the data rendered on your specific screen.
Okay.
Underneath those letters, there is an entire invisible ecosystem of hidden instructions and encodings that your text editor is interpreting on the fly.
Wait, really? Invisible instructions?
Oh, absolutely. Let's look at one of the main things Eng has to fix, which is line endings. When you hit the enter or return key on your keyboard, the computer doesn't just magically push the text down.
It doesn't.
No, it inserts an invisible character to tell the machine to start a new line.
So hitting enter is actually typing a hidden letter.
Functionally, yeah. Yes, it is. And historically, the tech industry could never agree on what that hidden letter should be.
Of course they couldn't.
Right. It goes all the way back to physical typewriters. On a typewriter, moving to a new line required 2 mechanical actions.
Okay, I think I remember this from old movies.
Yeah, you had a carriage return to push the roller back to the left side of the page and a line feed to roll the paper up one line.
Right, the ding and the slide.
Exactly. When computers came along, Windows operating systems decided to keep both actions. So hitting enter on a Windows machine inserts 2 hidden characters, a carriage return, and a line feed.
Wait, let me guess. The other operating systems did something completely different.
Oh, of course. Early Mac operating systems decided they only needed the carriage return character. Unix and Linux systems decided they only needed the line feed character.
Oh boy.
So if you take a seemingly simple plain text file created on a Linux machine, which only uses line feeds, and open it on an older Windows machine that expects both characters.
The Windows machine just doesn't recognize the instruction.
Exactly.
Yes.
Suddenly, your beautifully spaced 20-paragraph document is rendered as one giant, unreadable, continuous block of text.
Oh, wow. So the letters are identical, but the hidden mechanical instruction just gets completely lost in translation.
Yep. And that is just line endings. Ang also mentions the critical need to ensure UTF-8 character encoding and to strip out invalid characters.
Encoding, like how the computer reads the letters.
Basically, before standardized encodings like UTF-8, computers use different dictionaries to translate binary code, the ones and zeros, into human letters.
Okay, that makes sense.
So if a text file was saved using, say, a Japanese encoding dictionary, but your computer tries to read it using a Western European dictionary, the computer blindly maps the binary to the wrong letters.
So that is when you open a file and it's just full of bizarre, garbled alien symbols.
Precisely.
It's not that the text is corrupted, it's that the computer's reading it with the wrong translation book.
The underlying binary is totally fine, but the interpretation is broken. So when Ang says the goal of this code is to normalize the text, they're talking about creating a predictable baseline.
Okay, I think I get it. So an unnormalized text file is kind of like a junk drawer in your kitchen.
Oh, I like that. How so?
Well, from the outside, you point at it and say, oh yes, a simple container. That is the drawer. But you pull it open, and inside it's full of mismatched paper clips, dead batteries, loose screws, and like a rubber band that's melting into a sticky puddle.
That is painfully accurate.
It's technically contained in one place, but structurally, it's an absolute mess.
The junk drawer is the perfect way to visualize it. The operating system says, yes, this is a text file. But inside, it is full of unseen variations.
Right.
So normalization is about taking that junk drawer, throwing out the dead batteries, which are the invalid characters, making sure all the paper clips are the exact same size.
Right.
Those are the line endings, and translating everything into a single universal dictionary, which is UTF-8.
Because if you don't clean that foundation, any ebook you try to generate from it later is going to be fundamentally broken.
Exactly. It'll be a disaster.
But how does Ang actually go about cleaning out that junk drawer? Because it's not like they're just opening the file in Microsoft Word and clicking Find and Replace 100 times.
No, they are doing this programmatically. And based on the code snippet provided in the post, Ang uses a tool called pandoc, specifically calling a function named doctopandoc.
Pandoc. I'm not familiar with that one.
Pandoc is incredibly powerful in the developer world. It is essentially the industry standard Swiss Army knife for converting documents from one markup format into another.
Oh, nice.
Yeah, it handles the heavy lifting of reading the dirty input.
But the really fascinating part to me is what happens after Pandoc reads the file. Ang doesn't just fix the hidden characters in the raw text.
Right.
Ang actually writes the final file from what they call a customized AST. And AST stands for Abstract Syntax Tree.
Yes, it does.
But why do we need a tree? Like, why can't a programmer just write a quick script that says, find every weird character and delete it?
Well, because simple find and replace operations, often called regular expressions or rejects, are incredibly dangerous when dealing with structured documents.
Dangerous how? Like deleting the wrong thing.
Exactly. If you write a script to find and replace a specific word in the title of a document, a simple text parser might accidentally replace that same word every time it appears in the body paragraphs, completely ruining your text.
Oh, because it can't tell the difference between the title and the body.
Right. A raw text file is just a flat sequence of characters. The computer has no idea that the first 20 characters belong to a title and the next 500 characters belong to a paragraph.
It's just a continuous blended smoothie of data. Everything is mashed together into one liquid.
That's a great way to put it. But an abstract syntax tree changes that entirely. Parsing text into an AST means the program reads the flat text and rebuilds it in the computer's memory as a hierarchical tree.
So if the raw text is a blended smoothie, the AST is like a magical machine that reverses the blender.
I love that.
It takes the liquid and separates it back out, so you have a whole strawberry over here and a whole banana over there. You can actually inspect the ingredients individually.
That is exactly what's happening. And we can see that exact separation in the code Ang shared. Ang defines a document as being made up of two distinct branches on this tree.
Okay, what are they?
Metadata, which they call meta, and structural components they call blocks. Those blocks are further categorized. Ang's code specifically highlights objects like block header and block paragraph.
Oh, so the AST has successfully identified, hey, this chunk of text here, this isn't just a string of letters, this is a header.
Right.
And this chunk down here, this is a paragraph.
Exactly. By transforming the text into an AST, you can apply targeted logic. If you want to change the line spacing on every paragraph, but leave the headers completely alone, the AST makes that trivial.
Because they're on separate branches of the tree?
Yes. You just tell the program, traverse the tree, find all the nodes labeled block paragraph, and apply this change. You avoid the danger of accidentally altering a header because the tree strictly separates them.
Wow. Ang even mentions that they ensure metadata is prepended if it's missing.
Yeah, that's a crucial detail.
So the AST allows you to intelligently inject new information into the exact right structural location rather than just, blindly pasting it at the top of a flat text file and hoping it doesn't break anything.
It completely elevates the text. It goes from a passive string of characters into an active structured database that can be manipulated with surgical precision.
Okay, so we've taken our dirty junk drawer text file, we've thrown it into the reverse blender.
Yep.
We now have this beautifully organized abstract syntax tree in the computer's memory, where everything is cleanly categorized as a block header or a block paragraph. We have our separated strawberries and bananas.
All nicely sorted out.
But Ang's ultimate goal with this specific blog post is to output a new, clean TXT file. We have to put it all back together and write it to the hard drive.
Right, the final export.
And this brings us to the actual Haskell code Ang shared and why Haskell as a language is particularly suited for this.
Ang describes this specific part of the code as straightforward, which really highlights the unique philosophy of Haskell.
I mean, it didn't look totally straightforward to me at first glance.
Well, they explicitly note that the code leverages two powerful concepts, which are function composition and pattern matching.
Okay, let's look at the generate text function Ang wrote. It takes those blocks from the AST and converts them back into lines of text.
Right.
When I look at the code for pattern matching, it seems like a filtering system. But how is pattern matching different from just writing a standard if-then statement like you would in, say, other languages?
Well, in traditional languages like Python or C++, an if-then statement usually evaluates a Boolean condition at runtime.
Like asking a true or false question.
Exactly, like asking, does this variable equal the number 5? Pattern matching in Haskell is far more structural.
Okay, how so?
It allows the code to look at the literal shape or the type of the data structure it is receiving, and then execute different instructions based on that specific shape.
Is that like a bouncer at an exclusive club checking IDs at the door?
I like where this is going.
So the bouncer, which is the generate text function, looks at a piece of data coming down the line. It doesn't ask a yes or no question. It just checks the structural ID.
Right.
Oh, your ID says you're a block header. You go to the specific line over here. Oh, your ID says you're a block paragraph. You go to that line over there.
That's a great analogy. Taking that further, the bouncer isn't just directing traffic. The bouncer is actively unpacking the data based on the ID.
Oh, really?
Yeah, you can see this explicitly in Ang's block toLines definition within the code snippet. There's a line that says block toLines parenthesis block header underscore underscore txt equals bracket tl.to strict txt.
Okay, that's a lot of syntax. What does that actually mean?
That is the bouncer saying, because you are structurally a block header, I'm going to reach inside your structure, extract the raw text payload, and make it strict text.
Wow.
And the very next line is almost identical for block paragraph. It just extracts the text.
So the code handles each structural block uniquely based on its pattern, actively stripping away that structural ID badge from the AST and just letting the pure text through.
Exactly. And that leads directly to the second concept Ang mentioned, which is function composition.
Right.
If pattern matching is the bouncer organizing and unpacking everyone at the door, function composition is the assembly line inside the club that processes them.
Let's walk through that assembly line because the code is actually quite visual once you get used to it.
It really is.
It shows the metadata lines and the body lines being stitched together. It says meta lines plus body lines, so it's combining those two lists of text.
Yeah.
But then it pushes that combined text through a series of specific commands.
Right. In imperative languages like C++ or Java, to process a list of text blocks, a developer would typically have to write a for loop.
Okay.
They would have to create temporary variables, track the state of the loop, process each line one by one, and manually append it to a new file buffer. It can take 15 lines of really clunky code.
That sounds tedious.
It is. Haskell uses a declarative pipeline instead. You declare a sequence of transformations, and the data just flows through them seamlessly.
Like the t.unlines command, which stitches the separate lines back into a single document block,
Exactly.
and then it hits encode UF8. There is that universal translation dictionary we talked about earlier.
There it is.
The assembly line forces all the text into that clean, standardized UTF-8 format, ensuring no hidden encoding errors survive.
And right after that, there's another crucial command Ang uses in the pop line, which is intercalate empty string.
Yeah, I saw that. What does intercalate actually do to the text?
In this specific context, it takes the list of blocks, the headers, the paragraphs, and systematically inserts a specific element between every single one of them.
Okay.
By passing it the argument of an empty string, intercalate is inserting a clean, empty line between each block.
Oh, so it is literally building the physical spacing of the document.
Yes.
It ensures that there is a uniform empty line between every single paragraph and header. It mathematically removes the possibility of messy, random spacing.
It perfectly standardizes it. The final step on that pipeline is BLL dot from restrict, which takes that perfectly spaced, cleanly encoded text and writes it out to the new file as a byte string.
That is incredibly smooth.
This entire sequence is why Ang calls the process straightforward. Through function composition, the data pipes through these transformations unlining, UTF-8 encoding, spacing, converting to a byte string in one elegant, continuous flow.
There are no iterative loops to break or, temporary variables to manage.
Nope, none of that.
It really is elegant when you break it down. It takes the chaos of the junk drawer, maps it structurally with the AST, processes it intelligently through pattern matching, sends it down this declarative Haskell assembly line, and outputs a perfectly clean, normalized TXT file.
It's beautiful, really.
But it's a massive journey just to output plain text. And remember, this is only part 169. Ang is not done yet.
No, this is just the foundational infrastructure. You have to build a clean pipeline before you can build the complex features.
Right. Ang signs off this post by noting that this is just the initial TXT export implementation.
Just the beginning.
Yeah. In the upcoming post, presumably part 170, Ang plans to discuss the actual normalization and transformation steps in detail.
Which will be fascinating.
Now that the text can be safely pulled apart and put back together without exploding, Ang is going to start adding those specific filters they mentioned earlier. Filters to clean up white space, definitively reformat paragraphs, and perform additional text processing.
They have built the sterile clean room, basically. Now they can start doing the delicate surgery on the text itself without any fear of contamination.
I think that is the biggest takeaway for anyone listening to this. Ang's meticulous process is an absolute masterclass in preparation.
Truly.
It would be so tempting, especially if you were working on a deadline, to just try and write a quick script that uses find and replace to fix a few obvious errors.
Oh, people do that all the time.
But Ang took the time to build a robust system using Pandoc, to map the structure with an abstract syntax tree, and to leverage Haskell's unique paradigms to handle the data intelligently.
Because knowledge is most valuable when it's understood and applied. Whether you are coding a complex application or, frankly, just organizing the file system on your own laptop, taking the time to truly normalize your inputs saves you from massive headaches later.
Absolutely.
Standardizing how you receive and process raw information saves you from cascading chaos down the line. It is the ultimate preventative maintenance.
You clean the text so the text doesn't break your system. And that actually brings me to a final thought I want to leave you with. We have spent this entire deep dive talking about how incredibly hard it is to get two computer systems to simply understand a plain text file without errors.
Yeah, it's remarkably difficult.
It requires deliberate translation, mapping the structure through an AST, filtering out invalid characters, and standardizing the encoding just to ensure that a basic paragraph remains a paragraph.
It requires immense, hidden, mathematical effort just to maintain basic clarity between machines.
Right. So if our simple digital text requires this much deliberate normalization just to be properly understood, how much dirty data and unseen formatting errors exist in our everyday human-to-human communication?
Oh, that's a heavy thought.
When we talk to each other, how many unseen assumptions, differing cultural line endings, and incompatible character encodings are causing our messages to arrive garbled and broken in the other person's mind?
Probably a lot more than we realize.
Exactly. What would a normalization filter for our own daily conversations even look like?